everyone. We're going to start the workshop now for location. So this is our second workshop, and today we'll be going over training with. Oh yeah. So in case you guys aren't aware, ACM has a Discord. All the slides are posted on there. We also post it on the regular ACM Discord, but all right. So here's what we're going to do today. We're obviously going to cover KNN flavors, then we'll play a fun fruit. We have candy this time, and then we'll go over a short Python demonstration. Sound good? All right. So you're taking a walk in the sculpture garden, and you see this. Does it purr or bark? So that's our goal today. We're going to try and figure out what is this creature. Does anyone have any idea how you would begin to figure that out? Like, what were you looking for?
Maybe the nose.
A nose? That's one, yeah. Like if dogs and cats have different types of noses, and you compare this one, yeah, that's one option. The ears? You can't really see them in this image, but yeah, that's another one. You'd look at the shape of the ears, for example. The tail? Well, we have no data on that, but yeah, that's another one. I can't really tell, but perhaps that's another one. So all of these are characteristics, right? We assume that, or we know that dogs and cats have different types of these same characteristics, so we can use that to try and classify this, whatever it is. So what you guys just described are called features. There's some property of the thing you're looking at that describes what we're looking at, that can define what we're looking at. So for example, another one that wasn't mentioned is how sharp its claws are, I guess. And then the answer that we're looking for, aka is it a dog or a cat, we just call that a target or a label. So it's what we're trying to find out. So therefore, in our current example, we try and find out was that creature a cat or a dog. And cat and dog is the target. All right. So does anyone want to list out some other features of cats or dogs that could be used to help us in this case? Like what would you look for? Like what's different between them? Okay. I guess
you guys must be really bad at biology, like cats and dogs. Like, come on.
It's not really true. I suppose so. If you wanted to look at an average, perhaps, but as you said, yeah, some dogs can get really small, but so are cats. So maybe, but you're on the right side. Anyone else? Okay, want to go to the next slide? So we have some examples here that you guys listed already. So we talked about claws. Cats have sharp claws. Dogs may not have as much. Someone mentioned ears earlier. And then we discussed that they make different noises. So that's kind of what we do to figure out what we're looking at. So, in our case, let's say we gathered, like we went on the internet or something, and then we gathered a bunch of samples of cats and dogs, and we can put them in a graph that kind of looks like this. So each little animal would be a data set. So in this case, we're looking at two features here. How sharp are the claws, and what size are the ears? So by doing that, we're able to order our samples in a way where we can kind of see where the animals that we saw are. So cats, you see that they're all in this top left corner with sharper claws and shorter ears, and dogs are on the other one. So we're going to categorize our sample as this triangle. Does anyone have a guess? Where would you categorize this sample based on this graph? Just intuitively. 50-50 chance. So if anyone wants to raise their hand.
There's candy.
Okay, cool. You categorize it as a dog. What made you say that?
I mean, it's going away, right?
Yeah, it's close on the boundary, so you could arguably
burst.
in our case, we're going to classify it as cat. Oh, nice. Yeah. So in this case, we're going to classify it as a cat. And obviously that was just intuition, so we're going to go in on why we would call it a cat based on this specific graph. So let's go to my slide. Oh. Summarize. The reason why you say it was a cat or a dog is you want to look at the points that were closest to it, and then you pick how many were in this radius, and then you use that to classify it. So inherently, what we're doing is we have a bunch of known data, and we're trying to compare it to this unknown sample, and whichever one is more similar is what this new data point is classifying. So you see in this circle, we have this unknown, and if we just look at the nearest points, we can kind of get an idea of what is closer to or what does it mostly come to. Does that make sense, everyone? All right. So just a quick note: our outputs are categorical in this case, so it's not a complete. We're just looking at certain features and not like a wide expanse. So we've kind of gone over this.
Not bad.
It's okay. We've kind of gone over this intuitively, right? Like we just have this random feature. What do we think it is? But this is actually something that we're going to use in machine learning to quantify it. So now we're going and now we're just going to go over what we discussed in more complete terms. So we're just going to call this the KNNs point. Our new point, we're just going to give it a name to make things easier. We're just going to call it P. Can everyone in the back hear me, or is the fan too loud? Okay, good, cool. So we're going to look at the classes of the KNNs point, and K is just a number. You can pick that number. And now we're going to determine the class that is the most common among the KNNs points. I even know if any of you guys could do that. And then we can just determine that P belongs to this class that is the closest to. Does that make sense to everyone? Okay. So now, what's a neighbor? My neighbors all put passes on the Wi-Fi, so I guess I don't have it. Next one. All right. So as we saw from the cats and dogs graph video, we put everything on a graph that you might be pretty familiar with, which is 2D. You got x-axis, y-axis. So this is a three-dimensional space, and so therefore, in order to determine how close a data point is to other points, we can just use the coordinates to take the Euclidean distance. So essentially, you just subtract the x's from each other, y to square, and square root of the whole thing, and then you just have a distance, which in a way is kind of like how similar is it. So in the graph that we used earlier, when we had the claws and ears, if an image was closer to another one, it meant that it had similar length of claws and ears. Does that make sense? Okay. All right. So now we know what neighbors are, which is the space or the distance in the graph. So what's the nearest part? So essentially, we want to look for the neighbors that are closest or have the minimal Euclidean distances to the point we're trying to target. So essentially, it's just how close is it on the graph. All right, and now finally, the last part of neighbors. We covered neighbors, we covered the first K. It's just a hyperparameter, aka we can just choose anything, and then we can pick how many data points we want to sample in order to decide what our new finish belongs to. Okay, is everyone good so far? Anyone have any questions? Okay, so now how do you do that? We have a number, right? We have our graph and we have everyone in the graph. So how do we figure out what this new point is? So essentially, we're going to pick a point. We have its coordinates, x and y. And then we just want to see how far this point is from everyone else to determine who is the closest, because we need to sample where it is in the graph. And then once we've calculated how far this new point is from everyone else, we want to pick the k nearest points that have like the shortest difference between distances, and then we can use that to say, okay, our new data point is the most common class out of all these systems. Okay, so just to recap, because that might have been a lot. Essentially, we have a couple steps. First, we're going to say, okay, how many points do you want to look at? That's 10. And then we just go to each and every one of these points and then calculate the distance between them. And then we just order them, essentially. And yeah. So after we calculate distances and we order them in like least to greatest, then we can determine, okay, who's closest to our point. So essentially it's these three, if we're looking at k equals 3, because they're the closest point. And then we can just look at what these points have been classified as, because we already know that. And then we can say, okay, this is what our new point B is. So just to check, and we have Candy if you want to answer this. We're going to say our new point, our new cat or dog is its green point. What should the green data point be? If you can a little bit. Want you?
Or I'm gonna give candy to anyone who raises their hand. So even if you don't get called on, you'll still get candy. So
Okay? Yeah. Do you want to explain your answer?
Damn, good accuracy.
that was less good with accuracy.
Yeah. So if you want to draw a little circle around this, you can look at the three nearest points. So in this case, we got one red, and a blue. So it's 2 red versus 1 blue. So yeah, the correct answer is red. Thank you so much for that. And with that, I'll hand it off to Zachary.
All right. So far we have talked about what KNNs kind of do, right? So we're looking at the k nearest points. We find the most common one out of those, and then we say that is our label for our unknown value p. But how exactly are we going to choose the k value, right? So if we go back a slide and we look at this, if you were to choose, maybe if there were more blue points up here and you chose k equals 3, would that affect the answer here of what you say the green dot should be classified as? Any takers? No, right? Because you're still going to be looking at only these 3 points. But if I give you a value that maybe says like k equals 20, and there are a lot more blue points up here, that would affect your answer. You would probably classify it as blue, right? Because there are more blue points. So one of the biggest things we need to do is we need to figure out how we want to choose that k value to get the right classification. So this is another example, probably more clear. Right here we have this question mark. At k equals 3, what do we classify it as? Green. And then at k equals 7, what will we classify it as? A star, right? So once again, that's kind of the importance of choosing the right k value. Now, you may be asking, what is the correct value of the question mark? At k equals 3, it's a green triangle. K equals 7, it's a red star. Which one is right? We don't know, but in a real life example, what you would do is you would say, at k equals 3, I have 98% accuracy. And at k equals 7, I get 50% accuracy. So which one do you probably want to choose? K equals 3, right? It's more accurate. And so one of the best ways that we can tell which k value we want to choose is through experimentation. But there are some general rules that we can follow to start off with a pretty decent k value, and then go try different values and see which one gets a better result. So we are now going to think about 2 questions, right? I kind of talked about these a little bit, but what happens if we pick a k value that is too low? So think about the data set and how that can affect our possible outcome if we choose a really small k value. Does anybody have any thoughts about that? Once again, there is candy, but everybody will probably end up getting candy today. Any takers? It's okay if you guys are wrong. I'm probably going to be right, but go ahead.
Maybe if it's like too low, like 1, then you only have 1 data point. That's just not enough data.
Mm-hmm.
So like it's not a useful number really.
Yeah. So that's right on point, actually. So when you choose a really small k value, you're more prone to outliers, right? So the example that he was saying, if you were choosing k equals 1, you're only looking at 1 data point. But what if that 1 data point is a red dot in a sea of blue dots? It should probably be a blue dot then, but you're going to classify it as a red dot. So with a really small k value, we are very prone to outliers, right? Skews in our data that will throw our answer off. And now, so we probably don't want to choose a k value that's too small, but what would happen if we choose a k value that is too high? What would end up happening? So as an extreme example, think of what happens if you choose k as the size of your entire data set. What would you end up classifying any point as in that case? Yeah. You have a thought?
Yeah, because if you did count for all of them, then wouldn't it be actually more accurate?
Not necessarily. So anybody? Yeah, go for it. Yeah, exactly. So what happens is if you choose k as the entire size of the data set, you just have to look at the data set and be like, this is the largest number of blue dots. So let's say I have 20 blue dots and 19 red dots in like some clustering of some sort. If I choose all of them, I'm always going to classify any point as blue only, right? We're not going to get any fine-grained distinction between certain boundaries, you know, where the red dots and blue dots kind of exist. So now we talk about the general rule of thumb that we follow, and that is k is equal to the square root of n, where n is the total number of data points. And so that is just a general rule to start off with. You say like k is equal to this value, and then you go on to the experimentation as we were talking about to see which one gives you a better result. Now, there is one really important thing here, and that's that we want to choose an odd value for k. And why is that? So can anybody, oh, it's up there. Yeah, go for it.
Because if you have to be the number, then you're not going to determine which one.
Yeah, so basically you would have a tie, right? If you have like 4 dots, 2 of them are blue, 2 of them are red, doesn't really tell you that much. But with an odd number, you can always break that tie. So that's why we want to choose an odd value of k. And as this line right here says, this is a good starting point of k, but you should try different values of k to see which one gives the best accuracy and result. All right, so now here's a quick quiz. If there are 170 data points in your KNN algorithm, what k value should you pick? Sorry? C? 13. Can you explain why? Yeah. So just like he said, if you take the square root of 170, you're going to get 13 point something. So we're going to choose 13 because it's also an odd number, right? So it satisfies both of those conditions we were talking about, taking the square root, and then it's also a odd number. All right. So last week we talked about how like machine learning models train on data, and like they learn, and then they evolve and they become better. And you may be asking, with KNNs, all we're doing is we're really calculating a distance between points and then choosing the top, 10 numbers or whatever. So where does the training really come in, right? With KNNs, there is actually no training. We can just use the data set, right? As I was saying, we just calculate all the distances, and then we kind of have our answer. So this type of learning is called a lazy learning algorithm, right? Because we're not really doing any actual learning. We can just use the data set, calculate something from it, and get our result. We will cover eager learning algorithms a little later, but this is just some terminology. We refer to KNNs as a lazy learning algorithm. All right. Now, right here, I believe, is a KNN class. So like, you can run this on some data points and it'll return a prediction for a unknown value that you give it. But are there any pitfalls that we can identify for KNNs? Think back to the idea of like where we're deciding what our K value is. They're along those lines. What are some pitfalls of KNNs? Yeah, go for it.
I don't know if this is true, but if they are 2D models like an X and with just an X and a Y, you're only checking two categories or 2 parts of that. There should be a lot of dimensions to check.
Yeah, that is very true. Any other ideas? Yeah, go for it.
It's okay. Doesn't know where in the data set to count does K start to expand from in the data set?
So if we have like a data set of like 50 values, what we're going to do is we'll have an unknown point P, right? And what we'll do is we'll calculate the distance from those points to P for all 50 values, and then we sort them. So the ones with the least distance will show at the top when we choose the K top ones. We'll go over an example also. But say that answers. Yeah, go for it.
So like let's say you have like A equals to 3, the points that are far from it, are like the stars, and one close to it is like low, it will become like
Sure. Yeah. But that was that can result in some bias with our data. Yeah. Any other ideas? All right. Cool. So pros. There's no training required. You know, it's pretty fast with smaller data sets. That is this bullet point, and it's very easy to implement, right? All we're doing is we're calculating a Euclidean distance, and then we get our result. We do some sorting, take the top K values, and we get our answer. Now, here are the cons. It does not scale well to large data sets, right? If you have too much data, it becomes a lot harder to find those boundaries that KNNs start to try and look for. The other thing is the curse of dimensionality and computationally gets very, very expensive. So as he was saying, the KNN examples that we've been doing only deal with 2 dimensions, so like 2 features, right? But we can still calculate the Euclidean distance in multiple dimensions by adding different features. And so one of the examples that was brought up is, you know, maybe you have more than 2 features. What are you going to do? You may have like a 3-dimensional space, right? An X, Y, and Z. We can still calculate that. But as we add more and more features, the computation required to calculate that distance for all those data points is really, really high. And so that is what all these fancy terms mean for large data sets and for, you know, very high dimensions, you know, where we're going like 4 dimensions, 5 dimensions, so 4 to 5 features, it starts to get worse and worse. And so that idea of like where it's simple to implement, there's no training required, so it's a little faster, doesn't really hold anymore. All right. Now we're going to do a case study. So we're going to have like 20 data points, and we're going to go through how a KNN model would actually classify everything and do its calculations. All right. So we're going to work with a 2D example. So we have our X and Y and then the labels, right? So labels are 0 and 1. In this case, you can think of a 0 as maybe a cat, a 1 as a dog. We're just assigning something into 2 different categories. One important thing I forgot to mention, KNNs only work on categorical data, right? We're trying to classify something. Can't really do anything continuous with KNNs. All right, so here, X and Y, to reiterate our terminology, are our features, right? These are the 2 things that we're kind of considering, and then these are our labels. All right, so given this data set, what we're going to do is we're going to classify this viewpoint P as either a 0 or 1, and that's our point P right here, 57 and 170. So the first step that we're going to do when any KNN algorithm will do is we are going to use the Euclidean distance, right? We have our distance formula from a couple of slides ago, and we're going to go ahead and calculate that for every single point in our data set. So you guys are lucky. You don't have to calculate all the Euclidean distances. You're welcome. I did not write these either, so I'm happy that I don't have to do it up here. But what we have is we have all our distances with respect to our point P, right? So we take 58, 169, and was it 50?
170, I think.
Just go back a slide.
170.
57 and 170, and calculate our distance. So the distance between those 2 points is 1.4. And we're going to go ahead and do that for all of our different values, and these are the results we get. And now, if you count the number of data points we have exactly 9 data points. So what does that mean our K value has to be? 3. And so, square root of 9 is 3. It's an odd number. All good. And next slide. So now, to find the K nearest neighbors, we're going to need to sort our table by each sample's distance to P. And so this part is something you cannot forget. So we have all the data sorted in both the previous slides, and that does not happen in a real world situation, right? Your lowest distance may be somewhere at the bottom or in the middle. So you need to sort your data so that the top K smallest numbers are at the top, right? So then what you do is you just take your top 3 numbers in this case, because that's our K value, and we will use those to classify it as a 0 or 1. So in this case, what would we classify our new point P as? Yeah, 1, right? So these are our first 3 distances, 1.4, 2, and 3. 2 of them are 1, and so that's the most common answer we're getting. We're going to go ahead and classify it as a 1. All right, a recap again. So given a data set and a new point to classify, we're going to compute the distances between that point and all of the data in our training set. Then we have to sort the data set by the smallest distances. We take the top k values and we find the most common occurring value in those top k values. And that is what we use as our classification. Do we have any questions so far on how KNNs work and all of that? All right, cool. Next one. All right, more math, not really much, but the importance of data normalization for KNNs. And so when you're going out and sampling in the real world, you may not get that perfect scatter plot with like these nice distinctions between different features or different labels. And so we need to look at how we kind of maybe want to normalize our data or change it a little bit to help our KNN become a little bit more accurate. So in this data set, we just see almost a vertical column of red and blue dots. And can any of you come up with any ideas why this would make our model perform suboptimally? Yeah, exactly. So right here, all we're really doing is considering the value of x2. And we don't know how important the feature x1 is. And if our data looks like this, if we have, some point here, we don't know how x1 is going to affect it. And therefore, this is not going to be a good data set to run our KNN on as of now. And so the one thing that we have to do is we have to do something called normalizing the data so that we make it look a little bit more distributed and our KNN can perform better with its classifications. Do we have any questions on why we may want to normalize the data set to make KNNs work better? All right. So how do we normalize our data? So all of these look like fancy terms. It's not that bad. F is one of our features, right? So think of in the previous example, it's our x or kind of y-axis. The mean u is the mean value in that column, right? So we had all our y values. We would take the mean of those y values, and this is the standard deviation of that column. Some statistics terms. And what we do is for every data point in that column, we're going to apply this formula. We do f minus mu divided by the standard deviation, and that is how we normalize our data so that our KNN can perform better. So keep going to the slide. So once we apply this normalization, we get this data set. It's just slightly altered. The data doesn't really change. The data does change, but it still preserves the properties of the original data, right? So the idea is now we can classify this point much better than we could over here because we actually can care about our x1 values now. Instead of being like x1 does not matter, why do we even have that? All right. Any questions so far? All right, cool. All right. Ethics. So any questions on KNN so far? Because we kind of wrapped up talking about KNNs, and that is your first machine learning model. It's really simple to implement. But do we have any questions? All right, cool. So today we're going to be talking about bias in data, and it's really nice that we actually paired this up with KNNs, and you'll kind of see why, because we were talking about how data can be very biased with KNNs. But as a quick recap from last time, this is the ML pipeline. We have data, training, and model, right? And so this time our ethics portion will focus on the data portion. We'll be looking at how data collection can influence certain biases and stuff like that. And then as a quick recap, again, Candy is offered. Can anybody tell me about the 3 parties that we talked about last workshop? Developer, deployer, and user. And the names are, you just have to give me the definition of each name. Like Google the definition, and that will still be probably right. But
You can
yeah,
also guess.
that is also completely valid. All right, oh, this one is a little weird, but so developer, people who develop the ML models, deployer, people who actually put that model into a real world situation, and the user, people who interact with that model. Gave this example last time, Facebook ads. Machine learning engineers at Facebook, they're the developers. Facebook itself is the deployer. They're putting it on their platform, and users are you guys, people who interact with Facebook and those ads. All right, cool. Now we get to some more actual ethics this time. So AI models can be biased when collected data does not accurately represent the problem at hand. So data collection was not representative. Data reflects bias that is already present in society. So when we're talking about KNNs, what are we exactly doing? We are looking at its closest neighbors, right? So we're looking at the population that is most nearby it, and we're classifying based on that. Now, the question that we're going to ask is, what happens if that population was already biased? Your result will also be biased. So this is actually one of the issues with KNNs. Data bias, will screw up your results. And your KNN model will also be very, very biased, right? KNNs reflect exactly what the data is showing you. So that is really important to think about when you're dealing with KNNs, right? Because you're classifying it based on data you have and based on its closest neighbors. So if your closest neighbors are skewed, your answers are going to be skewed and probably prejudiced too. So there are two big examples. The first one is Compass, and this was used as an algorithm to predict whether a defendant would be rearrested for a similar crime. And it predicted twice as many false positives for black offenders than it did for white offenders. So this is the idea where we're talking about, like, this algorithm did not use a KNN, but if it did use a KNN, you can see why, right? If you're saying if our data set is only contained more black offenders than white offenders, you're going to classify maybe more black offenders being rearrested, and that is not true. So we had twice as many false positives. That means it was wrong. And to note that this was actually used in courtrooms and stuff for a bit, and people's lives were dependent on this, right? They got a longer sentence because some random algorithm that was based on a bunch of biased data was like, this guy's gonna get rearrested. And that never happened. And so this had a very real world impact on real people. And so that is one of the biggest things we have to watch out for is bias in our data. So if there's bias in our data, that will carry over into our models and our algorithms. Another big one is Amazon. In 2018, Amazon scrapped its hiring algorithm. So they had this hiring algorithm that looked at resumes submitted over a 10-year period. And guess what? It did not favor women. It was biased and kind of discriminated against them. So because most of the resumes in that 10-year period before were submitted by men, the tech field was very, very dominated by men and still even is now. So all the resumes it was looking at were like, oh yeah, guy stuff, blah, blah, blah. And it started being biased against women. And there is some interesting terminology that was released about the rewarded words and penalized words. So here are some examples of rewarded words: hardworking, fraternity, engineer, director, and salesman. And then examples of penalized words were hobbies, member, Scripps College, fire, and Society of Women Engineers. And so I hope those words tell you enough about how biased that model was. And for your information, Scripps College was a liberal arts only women's college. So very, very biased. And once again, you need to think about how biased is your data, right? Amazon did not consider the fact that all of their resumes were mostly men from 10 years ago, and it led to a really, really bad model, right? And obviously that's just not cool or fair for anybody involved. All right, game time. That is, do we have any comments, concerns, questions about the ethics portion? All right, cool.
If anyone's interested in learning more about ethics, tomorrow, 7 to 8, Reber Fireside Lounge. There's an ethics talk. I'll be doing it. Some other people will be there. It's very interesting. Good job, everyone.
Does anyone want to explain why you chose this answer for candy?
Correct. Beautiful job. He said cats don't have scales, hooves, or fins, which is, if I know my cats, that's very true. All right, candy for you.
Watch out for the projector.
Sorry.
All right. Excellent job, guys. Next question.
All right. TL, Mai, and Sun.
Sin. Keep up the good work. Again, does someone want to explain how they got this answer?
Someone can also explain why the other three are correct.
Or not, correct, yeah. Or
Aren't,
not.
sorry.
So one of these binary variables to classify what we're looking at, and then it also doesn't take too many data. Like it doesn't work with large data sets or continuous ones. So KNNs are restricted to being discrete and
Yeah, they're best at small data sets. Not that you can't use them, they're
Yes.
best at small data sets. You can use them for large data sets, it's just not as efficient.
oh, I see.
So for anyone who didn't hear, KNNs are only good for discrete data, which means it has to be categorizing it for categorical inputs, and the rest are continuous.
Yes.
All right, next one.
Well, we gotta look at the
Ooh,
scoreboard.
movement. Tol, or Mai, and Sun. Good job.
All right, next question.
I appreciate the
How do
candy.
they classify a new image data point? Who knows? Could be any one of these.
Yay.
Yes, by using the distance algorithm to determine who its neighbors are that are
Yep.
nearest to it, and then basing on it how they're classified. Perfect.
All right. Wow. We have a very consistent leaderboard here. Okay, next question.
Why are they biased? This is important.
Born with it.
Order of the data doesn't matter as much as what the data is, or what the data is. So yeah, if you're feeding the AI a data set that doesn't represent the entirety of the yeah, it's fusing.
Yes.
For those of you who couldn't hear,
Oh.
the order of the data being fed in, it does not have a huge bearing upon things, but what is actually
You can't-
contained
yeah,
in the
exactly.
data set is much more important and can lead to bias.
And like, just to add on to that, if we're looking at KNNs, the order that we're feeding the model that data does not really matter because we're going to be sorting it based on the Euclidean distance, right? So the order of the data does not matter. It's just lack of representative data or pre-existing bias in our data. Even if the data is representative, society does have some bias and that data does represent that.
Oh, small
Ooh.
change. Tall guys are getting taller.
Still Tul, Mai, and Sun in the lead.
You can't do any better.
Like 10 years of even a lot of actors think is kind of building the bias of perfect example of things that
Yes. Yes. Perfect. So, as she said, if you didn't hear, Amazon is one great example. Women are being hurt by the bias in the Amazon's hiring algorithm because it's less likely to hire women than it is to hire men. And so, understanding that these are the sort of things can happen is very crucial to understanding the dangers of AI. So, very good job.
All right.
All right, no changes on the scoreboard.
Next question.
Continuous or categorical? Who knows? All right, who wants to explain why it was categorical and not continuous?
There's 5 categories.
Yeah.
Perfect. So as he said, 5 categories, right? You can either be a 1, a 2, a 3, a 4, or a 5. You can't be like a 2.5 in this model because see where it says discrete values? That's your sign. When it's discrete, it is not continuous.
I always wanted to go skydiving. That question's pretty accurate.
Oh, okay.
Ooh, big movement, big movement. TL or Tol, Mai, and Sun still in the lead, but Vic is now second place. Very cool.
Oh. Naman is another workshops officer who is
Apparently trying to build a puppy army.
yes. He wishes he were here.
He doesn't have the time to identify all the puppies in this area by hand, so he wants to build a program that will take in an image of an animal and output if it's a puppy or not. Categorical or continuous?
I think this one is. Oh, I hope no one. Okay. This is the question that was wrong, I think.
Okay. So there was a right and a wrong answer.
But it's not here.
We accidentally made it into a multi-select.
Oh well.
Does anyone think they know which one was the right answer? Why? Makes sense to me. Did everyone hear that? There's 2 categories. It can be a puppy or it cannot be a puppy. Ooh, big movement. Penguins in first. I think
Okay.
that might be our fault.
Yeah, that is totally our fault. Sorry, guys. Oh wait, is this my turn?
Yeah. All right. Claire is planning to go on a trip around the world and wants to get the most out of her money. She wants to build a program that will allow her to predict vacation prices for various countries throughout the year and use it to generate the most optimal vacation plan.
there's too many factors. And also we don't know what predictors they're using or like how many factors they're using to come up with their optimal. So it could be like a million numbers or yeah.
That's precisely it. Yeah, there's no set amount of numbers that my dream vacation will take. it could fluctuate based on the day. So it's not like you can divide it into categories. So yeah, that's correct. So sad.
All right.
Small change, small change.
Penguin's still on top.
I think this is the last question.
Yes, very important question.
Oh, is it? Okay. Thank you guys for playing. Third place we have Penguins.
Penguins. Woo!
Second place we have Vic.
Woo!
First place. Oh, they came back.
Woo!
All right. Thank you guys so much for playing. We got some runner-ups.
I know the pain.
All righty, y'all. So we're gonna get started on the coding portion. So
Oh yeah, the link is there.
the link is right here. This will take you to the notebook, and so it's tinyurl.com/knn-python-demo, and the first thing you're going to want to do is make a copy of it so you can have one for your own use, that you can make as many changes as you want to. So has everyone typed in the link? I'm going to take that as a yes. There's one person nodding his head. Oh, all right. That's a no. So give you guys a little bit longer. All right. Anyone else? We're all good. All right. I'm assuming we're all good. If you need, I can show you. All right. So it should look something like this. So if you go to File, save a copy in Drive, it'll do that. And then it'll open it up in a new tab. So this means this is the copy that you made in your Google Drive. And now we're going to get started. So has everyone made the copy? We're all good? We're all good. Awesome. So the first thing we're going to be doing is we're going to be importing a couple of libraries that we're going to be using for this demo. We're going to be importing NumPy, which is for like math and stuff like that in Python. We're going to be importing matplotlib, which is basically something that lets us plot our data. And then we're going to be importing a couple of sklearn things, which is basically for machine learning. It's a machine learning library that we're going to be using. So, and I'm going to be talking through this. If you guys have any questions, feel free to just raise your hand. I'm happy to pause, clarify, whatever you need. So the first thing we're going to do is we're going to load the iris dataset. This is a dataset that comes with, well, it comes with sklearn as a default like dataset, and we're going to be using this for our KNN dataset. All right. So we can go ahead and print out all the documentation. So this is just telling us a little bit about the data set that we have. So there's 150 instances, 50 in each of 3 distinct classes. There's 4 different attributes that are contained in here. That's sepal length, sepal width, petal length, and petal width. And then the types of irises are iris setosa, iris versicolor, and iris virginica. I think these are flowers.
Yes, they are.
Okay, they are flowers. And we can see here some more statistics, the minimums and maximum, the mean, the standard deviation, which in case you didn't know, the standard deviation is like sort of a measure of like on average, how far from the mean your data set is. You know, so if you had like a data set where like all your points were like either here or here, and then the mean was like in the middle, that would have a very big standard deviation. But if you had a data set where like all your points were clustered at the middle, the mean would be the same, but the standard deviation would be much less. And then class correlation. What is class correlation?
I'm not too sure how much it applies to what class it is, I suppose. So
Yeah.
the ones that are high probably are a good indicator of what class it is.
Yeah, so the ones that are high, good indicators of what class they are. They're very, very much correlated. And then there's a bunch here about licensing and then, references. So if we look at just the feature names, we can see that they're the same as the feature names we had up here, which are sepal length and width and petal length and width. And then the target names are setosa, versicolor, or virginica, because those are the types of irises that we're hoping to classify. So the first thing that we want to do with our data, now that we've had it all loaded in, we've poked around it a little bit, is we want to assign the features to the X and the targets to the Y. So the X-axis, or the X-axis is going to be like the data set of all these features, and then the Y is going to be the target, which is like, if it's setosa, versicolor, or virginica. Any questions? All right. So we're next going to be splitting our data into training data and testing data. So there's a very important reason why we do this. We don't want to be training with the same data that we're testing. Does anyone have any ideas why that might be? Yes.
So the y-axis is the target. Are you talking about
Yeah, when we go down later, actually it might be this very next one, then you'll get an idea of what it looks like. Yeah, you can just go ahead and get it.
like this is y-axis?
Oh, you are right. That is not the y-axis. The x-axis is the data which is going to be on the x and y-axes, and then the y is just referring to the corresponding target data. That's my fault. So any other questions? So to go back to my original question, does anyone have any idea why it might be a bad idea to train and test on the same data? It's okay, like you don't have to be right. Like I'm just looking for a guess. Hit the nail on the head, right? If you're training your data on some set of data and say it says, if you have a 5 centimeter petal, it's gonna be a virginica every time, right? And then you test it on the same data that you used to train it, that is just gonna confirm what it already figured out, right? And so you wanna see if this works not just on the specific data set that you fed in, but you wanna see if it works on other data sets. And so that's why you wanna make sure you save some of it to be used to test it afterwards, because this is data that it never got to look at. And so it can tell you a little bit better how accurate your model is. So does that make sense to everyone? All right, and then so here what we're doing is we're plotting the training data. These are all calls to the PLT library. Like this is not super important for you to fully understand. Because this is just a way to visualize it. What's really important is understanding the actual KNN process. But any questions about that? All right, perfect. So we can then create a KNN model, which comes default with sklearn, which is one of the packages that we imported. And so the first thing that we do is we fit the KNN model to the training data, and we do that by passing in the X and the Y training data, and then the built-in sklearn library is going to fit the data for us. So,
Yeah, what's up? So I believe fitting data in this case is just analyzing where each of these points are. So we're building our graph essentially, so we have our graph now. And so once we have our graph, remember when we put in the viewpoint, then we can use it to categorize. We need to tell the, this is a class, I believe, what our data looks like, so it can then use that to plot viewpoints. Does that make sense? Oh, sorry. Okay. So you know how we were able to visualize all of our data points in this graph? We need to tell our class, our team neighbors classifier, what does our data look like? Because remember, there's no actual training for KNNs, it's just the data. So we need to tell our class what our data looks like in this 2D space, for example, just to like visualize for now. And then what we can do is we can add new points, and then it can use this data that we've given it to tell us about it. So it's essentially prepping it for prediction. Does that make sense?
Any other questions? All right. So because this is a built-in class that we imported, the hard work of having to go through and check, the figure out what a good K number is and figure out what the nearest neighbors are is going to be all done for us by this. This is going to make our KNN model spit out its predictions for our testing data based off of the training data. And this goes back to the same idea. We don't want to test and train on the same data, especially bad with KNNs, right? So now we can call the KNN score function, which is basically going to give us a score that tells us how accurate the KNN model was. So when it tested it, how often was it able to get it right? So we can see it was 0.98 accuracy, which means pretty good. That means, 49 out of 50 times it was getting the data right. So pretty good job by our model. And now what we're going to do is we're going to try and find the best K for this data set. So as we discussed previously, a good rule of thumb, a good heuristic, is that you want your K to be roughly the square root of the number of data points in your data set. But obviously, there's more fine tuning that can be done to get you greater accuracy. So what we're going to go through here is we're going to go through a bunch of different Ks ranging from 1 to 20, and we're going to use that K for each time and then calculate the accuracy of it. So we'll go with like 1 and it'll tell us what the accuracy is, then 2, then 3, and then at the end of that, we're going to say, okay, which one gave us the best accuracy, and then it'll output that. So if we run all this code, we can see that the best K is actually going to be 8 for us. So if we look at the 8 closest neighbors, our model has told us that that's going to be the most accurate. Now, as we probably are able to tell, we fed in, I believe it was 100 data points. And so 8 is pretty close to the square root of about 100, right? Off by a couple numbers, but obviously it doesn't have to be exactly that. Now, can anyone tell me why it might be okay for us to have an even number here, even though we said that we might not want to do it in the slides? This one's a pretty tricky question. Well, so normally what you're doing with choosing an odd K is if you're classifying 2 different things, you know that there can't be a tie, right? Because if you had like 8 data points and 4 of them were dogs and 4 of them were cats, you would have a pretty tough time figuring out which one it was supposed to be, right? But in this case, it's actually okay if we end up using an even number. Did you raise your hand?
Yes.
Yes, so it's a little better here. Like, yes, there still can be ties, right? But it's not as bad if we have more categories to have an even K number. Does that make sense to everyone?
Also, the best way to find a K value in the first place, like this is just a rule of thumb, but if you try a better value and it works like this case, then you might as well go with that, right? So that's just a good starting point, and then it's up to you to do some experimentation to decide what's the best K value for your data set, like we just did. Does that make sense?
All right, so now if we plot the data that we just generated, we can see that we have a couple plateaus, right? And the highest plateau is up here, right around, if you see what it's centered around 10, which if you guys recall, there was 100 data points, so 10 being the square root is right around the sweet spot for this, this model. And so if we call the X train, if we take the shape attribute and index it, it'll tell us how many data points we have, which is 100, right? And so this demonstrates that the heuristic of taking the square root of the number of data points is a pretty good idea. So I believe that concludes our demonstration. Does anyone have any questions, comments? Yes. I believe it's not necessarily inherent to like inherently good. It's just good for approximately modeling the behavior, because if you think about it, when you have like just a few data points, right, you probably want to be taking stock of like a fair number of them, right? Because, you know, if you only had like 9 data points, even though there's not a ton, looking at 3 of them is you probably don't want to be going like any like smaller than that, right? But then as you get into like bigger and bigger numbers, if you have like, I don't know, like 400 data points, right, you need to be taking a much smaller fraction of 200, right? Like with 9, taking about a third with 3 is like a pretty good idea. But then as you get into bigger and bigger numbers, the number of neighbors that you need to take advantage of doesn't really scale quite as much. Does that make sense?
First part of the checking prediction is that's based on a prediction, and you actually show a prediction to happen.
Yeah, that's what the testing is for, because you still have the label, so you're able to check on that.
All right, any other questions? Line 7. Oh, so basically X-train, right? So X-train is our set of training data, right? And then it has this attribute called shape, and contained in there, it's stored as like an array, right? And then the first, so if we index it to go to 0, the first value that's stored in the iterable object that stores shape is going to be the number of total data points. So like, you know, I'm not super familiar with the exact documentation behind it, but this is something where like if you poke around and like read about how these libraries work, you can figure out how to determine it. So or 0, so 0 doesn't tell you anything. So do you remember how in our Python demonstration you could index lists? So if you have like a list of a bunch of things, right? You can, if you want to look at like the first item, you do in brackets 0, which gives you the first item, and because you start counting from 0, and then, you know, if you do brackets 1, it'll give you the second item, and so on and so forth. Basically, X-train is storing like a variable called shape like inside of it, and then
I'm trying to figure out what the variable means.
the 0.
It's 100% accurate.
Oh, the 100 means that there's 100 data points that we're using in our KNN model. Any other questions? All right, well, if there's no other questions, that is it. Feel free to come forward, take some candy, you know. Any other questions that you don't want to ask in front of everyone, we're also here as a resource. Great work today. We're happy to see all of you.
Thank you so much for coming.
Yeah.
Thanks.